Thanks very much for your time, colleagues. This is Mike Anthony, from Ann Arbor, and I have our colleague from University of California, uh, Berkeley, on the phone on our call today, Jerry Jimenez, and a couple others. So what I'll first do is I will introduce, let Tammy and Kane introduce themselves, and then we'll let Jerry introduce himself, tell us what he does there, and after that, it's more or less his show. So Tammy, you want to say, this is Tammy Gammon from Georgia. Would you like to tell us a little something about yourself, Tammy?
Well, I actually did my PhD research on arcing ground faults, and I have spent most of my career working on them to some level, so I'm very interested in hearing what Jerry has to say today.
Great. I'll also say you're being a little modest. You are actually the contractor the uh, for the NFPA Research Foundation project, which hopefully will be presenting at the conference at next year in Boston. But as you know, and Jerry is actually a contributor to the data that help us get that code change in the 2014 NEC. So more on that later. Okay, thanks, Tammy. And Kane from Michigan State University, you want to say a little something about what you do there, Kane?
Yes. Good afternoon. This is Kane Howard with Michigan State University, and I'm an electrical project engineer here. Project engineer here, and I do a lot of low voltage stuff, some medium voltage, and a lot of lighting. And I'm getting more involved with standards and helping out with IEEE any way I can.
Great, thanks, Kane. And Jerry, okay, Jerry, why don't you say a little something about what you do, and then carry on. Carry on.
Okay. So I am the supervisor of electrical engineering here at UC Berkeley, and I work in what used to be called the physical plant department. They've changed names, but anyway, we basically do the operations and maintenance for the campus. Most of my responsibility lies in the 115 kV and 12 kV systems. I get a little bit involved with the transformers that step the voltage from 12 kV down to the building utilization level in the buildings, but I don't do much in the buildings. Although we have no other doublies here other than myself, so if something comes up, if the electricians need some help, then I jump in and help them with that. But my expertise is more in the medium voltage area.
Okay.
I've been here about 17 years. Prior to that, I worked for 22 years as a field service engineer for Westinghouse. So a lot of my experience is equipment-based, transformers, protective relays, current transformers, medium voltage switchgear, distribution transformers, and substation transformers. So when I came here, I started here in 2000 and saw we had the medium voltage grounding system. It was really nothing unusual to me. I'd seen many of these in my experience prior. However, I did some work at campuses, universities, colleges, and junior colleges, and even a few high schools in my prior career, but none of them had any medium voltage grounding systems. They were always solidly grounded. Did you want to say something, Mike?
Well, this looks like we have two others. Your colleague, Jim Murphy. Hi, Jim. Are you able to hear us this time? I guess not. Oh,
Yeah, can you hear me?
yeah. You're coming across loud and clear. You want to say a little something about? I guess you and Jerry haven't. You've been here. You're relatively recent, and so you guys haven't had a chance to get to know each other. I feel a little bit comfortable saying so, but Jerry, meet Jim.
No, actually, no, I know Jim very well. I've known him the whole time I've been here and then some. So,
Okay.
no, Jim and I know each other very well.
Okay, great. And let's see, have Lauren. How are you, Lauren? This is Lawrence from Alberta. Hi there, Lauren.
Hey.
So here we are. We've always wanted we seem to be getting one of these every month or so. So I'm very happy. It looks like we have three other calls. I don't have a name for them, so I'm just going to let them. We have 7 people on the call now. Caller number 2, 3, or 5. Do you want to identify yourself? I guess not. So, all right, then maybe at the end they might be having some technical problems, but at least I'm able to see all of you. So, Jerry, why don't you carry on with your presentation? Go ahead.
Okay. So I gave my introduction, but I'll go on to the next slide here. So that's our campus that we're very proud of, with the San Francisco in the background. That's the San Francisco Bay Bridge you're seeing there just beyond the Campanile, which is the name for the clock tower. It's more or less in the middle of our campus, and that's a pretty iconic structure. You can see it from many parts of the Bay Area, and it's been there since 1923, and it's one of the symbols or icons of the university. So that's looking to the west from probably up a little bit in the hills of Berkeley. Next slide. So this is the oldest building on the campus. It was built in 1886. There were several other buildings that were built probably at the same time of this building, or maybe even a little earlier, but they were destroyed by fire or earthquakes. As you know, we're an earthquake country here in California, and unfortunately this is the only one that remains. Now, the important part of this building is it was the first building to receive electrical power other than where the power was generated, and that was done in around 1894. So we had some pretty bright and pretty bright professors with a lot of foresight who were recruited to come here, and they early on jumped right into the development of power generation and power distribution. So looking through the records, they had a building called the Mechanical Arts Building, which was probably back then kind of a combination of all different types of engineering. They built their own little power plant, and they had coal, and they burned coal, ran a steam turbine, and they ran a 20 kilowatt DC generator. So I don't have any more records than that, but I'm imagining that that DC generator sent power over to this building here, South Hall. I do know that I found an old drawing, and I do know that they had three types of circuits. One was called power, one was called incandescent, and one was called an arc circuit, or circuit for arc lamps, which would probably be the exterior lights or external lights of the building. Okay, so next slide here. This building was built in 1904. It was the steam plant at that time, provided steam and electricity to the campus from 1904 to 1930. And just a little historical note, the exterior is noted for its WPA mosaic murals depicting street musicians and artisans. So that most people may know that WPA was a government program instituted in probably the 1930s to employ people who were out of work. The government had money, but nobody had jobs, and this was a way to get people doing something productive. So it's kind of a historically important building. Although around 1930 it could not produce all the steam that the campus needed. And certainly by that time the campus was purchasing its electricity from the utility. So in 1930 a new steam plant was built, much bigger, and that plant is still called the steam plant to this day. Around 1986, cogeneration was a hot topic, I know certainly in California and I believe all around the country, and the university decided to get into that. So they built, it meant an addition to the steam plant right over here on the left-hand side. That's called the cogen plant. So most of the cogen plant is in there. There's a big gas turbine about 25 megawatts and a smaller steam turbine about 5 megawatts. And of course there are lots of interconnections with steam and wiring between the old steam plant and the cogen plant.
So where's your exhaust heat coming from? We're not looking for stacks here, Jerry.
Well, they, of course, in the cogeneration, they take the waste heat from running the gas turbine and use that to use it in a heat recovery steam generator and use that to generate steam, which goes underground and gets distributed to the campus. So there's not a whole lot of waste heat. You see a little bit here. This is just the stuff they couldn't use.
That's pretty amazing. That's,
yeah.
Good for you. You're using every BTU.
They use as much as they possibly can. And oh, by the way, this is operated by a third party, so it's up to them to extract every ounce of energy that they can from the natural gas that they burn. So they do a pretty good job of doing that.
Well, that's very interesting. Well, we'll have a future teleconference on the buying, selling of campus power systems, something that's piqued the interest and inflamed the imagination of trustees and boards of regents and some all over the country. So I'm glad you pointed out that it is being run by a third party, although the university itself owns you own your power system and you're responsible for its operation and maintenance. Is that right?
Yes, that's correct.
So this is just a third party, a private contractor running the powerhouse.
Just for the power plant, yeah, the cogen plant, right.
Relatively easy to partition that. Okay, thanks. Go ahead.
Okay, so for me to really get into the whys and hows of why we went to the medium voltage ground, I need to talk about our neighbor to the east. So this is a nice aerial view. The UC Berkeley campus is surrounded there in the red outline. Don't have the whole campus there, but this was a slide taken from the Lawrence Berkeley Lab website. So the Lawrence Berkeley Lab is there, surrounded in the yellow. Two really important landmarks I want to point out. First of all, this building here that my cursor is on. And by the way, Mike, can you see my cursor? Hello?
I can.
Okay. So the cursor is currently over a building called the Bevatron, which stands for billion electron volts. So that was a device, an accelerator that could develop up to 1 billion electron volts. When I was in college, that was back in the 70s. That was a pretty big deal. That's a lot of juice. And we studied that in physics, I remember. That building has since been decommissioned and repurposed into something else. But a lot of historical significance there. A lot of really good research was done. However, even more importantly is this building here that I've got my cursor on right now, and I'll move it to the side so you can see it. That's the cyclotron. That building was built in 1931. It was the first cyclotron in the world, and it was built by Ernest Orlando Lawrence, who was the founder of this Lawrence Berkeley Lab. So yeah, I talk about here the marquee here, the LBL cyclotron built in 31, first one ever built. Now, it outlived its purpose sometime in the past. I don't know exactly when, probably in the 1980s or 1990s. So it was repurposed to a advanced light source building. They do lots of research there. I don't know a lot of details of it, but in real rough terms, what they used to do with electrons, they now do with light. They bend the light beams. They've got some huge magnets in there, and very impressive. They actually, I believe, they make their own magnets. They probably purchased the laminate iron from somebody else, but I think they actually wind their own magnets there, so it can do exactly what they want in terms of magnetic fields. Notable also is Lawrence Berkeley Lab is the oldest of the national laboratories. Again, it was founded in 1931. Important to note from how it operates, it's funded by the Department of Energy, the DOE. However, it's managed by the University of California. Also important to note, it's a completely separate entity from UC Berkeley. So UC Berkeley is part of the University of California system, but we are a standalone campus, UC Berkeley. Again, here's the cyclotron, and then you can see this marquee, the Campanile Clock Tower, and of course, beautiful view of San Francisco Bay. There's the SF Bay Bridge, which leads to Oakland, and then here's the Golden Gate Bridge.
Jerry, was there a strategic reason why this was located here? And not that I disagree with it, but just that, was it Professor Lawrence? This was his area where he where he took his residence or his education. Because you have Cal Berkeley in the farther south, of course, and I was just curious what the history is. How this landed here.
Yeah, unfortunately, I can't tell you other than Professor Lawrence was a professor at UC Berkeley before he started this lab. So,
okay. There it is.
Berkeley is a relatively old city, at least for California. So a lot of it had been developed already. Most of what you see over here was in existence way back in the 30s. The hill was probably just wide open space.
Yeah. Okay. Thank you.
Now I want to talk about the prominence of this Lawrence Berkeley Lab. I did not realize this myself until I did a little research for this presentation. 16 chemical elements have been discovered at the Lawrence Berkeley Lab. Of course, when I was taking college chemistry, we talked about berkelium. Being here in Berkeley was pretty neat. Californium and lawrencium, but there's lots of others. There's 13 other ones. So some of these were developed with the assistance of that cyclotron that I pointed out earlier.
Say, Kane,
okay.
You just got a national lab over there. Michigan State just got a lab. What's it called, Kane?
It's we got the cyclotron, and then we have the F-rib. That's the big thing, is the F-rib.
Okay, so do we see a Michiganium sometime in our future?
I'm sure hoping so.
Okay, go ahead, Jerry. How to get that in?
Okay, so So now we're going to start talking about electricity. So this is a UCB/LBL single line diagram from the period of 1963 to 1986. Again, I've only been here since 2000, so I had to kind of dig for some of this stuff or talk to people that had worked around here longer than I had. But it's very simple. You know, back in those days, things were very simple. We were serviced by the utility, PG&E, Pacific Gas and Electric. We had a line 1 and a line 2. Line 1 came in and fed our transformer, 115 kV primary, 12.47 kV secondary, fed our campus. The transformer was owned by the utility at that time. The primary winding was solidly grounded. Secondary winding was solidly grounded. And likewise, over at Lawrence Berkeley Lab, they had a very similar setup, same voltage ratings, same situation in that the utility, you know, was in charge and operated all this equipment here. On the other side of the dividing line was the UC Berkeley campus here, and then in its own little section was Lawrence Berkeley Lab. So it operated that way for a long time. I can't say too much about how well it worked because I wasn't here. Haven't heard about any real problems, though. Now, in the 1980s, as probably lots of parts of the country were growing, universities were growing, more research needed more power. Actually, I got a little ahead of myself with that statement, but what we did here was we purchased the substation from the utility company. So now this line of demarcation moved up a little bit on the page. So now we owned and operated this transformer that fed us, and as well as the other transformer that fed Lawrence Berkeley Lab. Nothing changed with the transformers, nothing changed with the winding configuration, still Y to Y, grounded both sides. But what we did was add this cogen plant that I talked about. That was 1986. So the cogen has a gas turbine generator, a steam turbine generator, and the question is always, how do you properly ground a cogen plant? And this is nothing that's really unusual. We've got a solidly grounded source up here at the transformer. It's usually a good idea to use some kind of a low resistance grounding or resistance grounding. In this case, it was done with the assistance of a zigzag grounding transformer. That's pretty consistent with what I've seen at other places. The idea, okay, so also important to this, the combined output of these two generators could be up to 30 megawatts. In 1986, when this was built, campus load was about 22 to 25 megawatts. So the thought was that if the transformer ever failed or if the utility failed, we would run the campus on these two generators. If the utility failed, we would lose this transformer. We would be separated from it by a breaker that's not shown here. So we have to have some kind of grounding, and so that's why another reason why we needed to have some sort of grounding for these generators. Have to account for the situation where the utility's gone and we're running on our own. So obviously we need to have some kind of grounding. Okay, so let's see. The next page, things got a little more complicated. This is where the lab was growing, the campus was growing, more research was being done, more power was being needed. There started to be complaints of power outages, so we wanted some redundancy. So UC Berkeley and the lab got into some joint discussions, and they went on for a long time on a regular basis. They're probably weekly or monthly. And they talked about how best to modernize this power system that was there. So this is what they came up with. The two transformers that you saw in the previous drawings now were going to be part of the Lawrence Berkeley Lab substation, which is called the Grizzly Peak substation. Two new transformers were going to be added, T1 and T2 here, and these were going to be feeding the Hill area substation. So now we have a little redundancy here. We each had two transformers, fully redundant, with lots of capability for fans to increase the kVA rating on the transformer, so we were both pretty well set. Actually, in reality, one transformer from our facility, is everybody hearing me okay?
Yeah, you're fine.
Okay, I hear a little echo. One transformer from our facility, either T1 or T2, could actually feed our entire campus as well as the Lawrence Berkeley Lab campus. We never had to do that, but just to give you an idea of the level of redundancy that we had. Now, in addition to having redundant transformers, somebody thought of the great idea to run a tie line between the two facilities. This would be at 12 kV. So we have a tie line number 1 here and a tie line number 2 here. So this gives us a little bit more capability. If Lawrence Berkeley Lab was in dire straits and their transformers failed or a main breaker failed, we could back them up by sending some 12 kV power over to them. I've drawn these two devices as switches, and I just did that to show that they're normally open. They're really circuit breakers that are normally open and racked out. So when needed, we do rack them in and close them. We've done all the synchronizing checks that needed to be done. We do have sync checks across these two devices here to make sure we can't close them out of sync or out of phase. Also, because
I'm sorry, how often have you actually had to use them?
Well, we've actually done it about 4 or 5 times, I would say, over 17 years. Mm-hmm. We've done it at a few times at the lab's request, not for an emergency situation, but for maintenance situations, or maybe some modifications that they want to do. They need to de-energize part of their sub or maybe all of their sub. And there's been a few times where we closed both these switches and basically fed all their power, through our system over to their system. Of course, they were separated from the utility up here. Because we've got this generation here, we have sync check relays in a lot of places, including these two. We have to always be conscious of power. There's a possibility if we open a certain breaker, we could have power coming in one direction from the cogen facility and power coming from another direction from the utility. So in those locations, we have these sync check relays that don't let us close the breakers back in unless the two sources are synced.
So how did this system perform during the earthquake? Back, I think it was 1988, 89, early 89.
So, that would have been this prior slide. Actually, that's a really interesting question. As far as I know, everything worked fine. However, there was some old 12 kV bus work over in this part. The old IPS copper pipe horizontal bus that was mounted on some really old insulators. One of those insulators broke, we think, during the earthquake in '89, and it took a while to evidence itself. But I'm told that in the late 1990s, probably around 1999, this was discovered, and one of those buses was actually drooping down because of the insulator being broken. It was a lot closer to the bus below it than it should have been. So they did actually do an emergency shutdown of this transformer, and they attempted to run the campus on the cogen plant. They were not real successful. I don't know all the details, but it actually dropped the campus during a few attempts. And I think they finally got it to run, and then they made this repair. So yes, when that happened, that made it a lot easier for us to go from this situation to this situation.
Yeah.
This cost a lot of money, and it did free up a lot of money. That was a big power outage when that bus dropped down and got close to the other bus. It happened during finals week, and it was May. A lot of people had their tickets arranged for their airplane flights to leave the next day after finals, and all of this had to be canceled. Finals were rescheduled. It was a mess. So that earthquake actually did help us to get this system that we have.
Every crisis is an opportunity. Sure.
Yeah, exactly.
Especially in an area where the upper management can't really comprehend electrical power. All they know is they're on the receiving end of complaints. So
yes.
Yeah, I mean, we're looking about, I don't know, $10, $20 million of investment here. Whatever the number is, I'm sure it was large.
Yeah, it was. I think our substation was $11 million. That'd be this T1, T2 plus everything that goes with it. And then we did a renovation of this substation. I'm guessing was $3 or $4 million.
Okay.
And so 10 to 20 was a good. Back in 1999, 2000, that was a round number. Probably more close to 20 million.
I think Jerry.
Go ahead.
That was during that renovation time is when those two 1247 tie lines were used, because we took Grizzly Peak completely offline during the renovation and kept the Lawrence Berkeley Lab was being fed completely by the UC Berkeley Hill area. So.
Yes, that's correct. Thank you, Jim. Yeah, so actually they did come in handy for that time. This whole thing was redone, so they couldn't get any power from the utility. So these tie lines were used for actually a pretty long time, a year or two if I remember right, maybe a little longer.
Yes.
So the important thing that is the topic of this conversation to note here is these transformers, 1, 2, 3, 4 of them, they all had this little resistor here between the neutral and the ground. And this is a good time to talk about why did that happen. So you got to see some slides that show how prominent this Lawrence Berkeley Lab is. When we as UC Berkeley, we're talking to Lawrence Berkeley Lab about how to best create a new power system. The Lawrence Berkeley Lab people really wanted to have a grounding resistor in the 12 kV system. They had, and they still have, some very sensitive instrumentation up there. It was their feeling that ground faults, when you have a solidly grounded 12 kV system, are very disruptive to the research instruments that are up there, both in terms of possibly damaging the instruments and also corrupting the data. So this resistor idea was really pushed by Lawrence Berkeley Lab. And again, I wasn't here when these decisions were made, but I'm told that here at UC Berkeley, we really had no problem with that because we thought it was a good idea too.
So you actually had to wait for a capitalization opportunity brought on by a crisis to get this out. You didn't have, well, first of all, to reel back, it looks like early in the 1860s, your professors already were using what were resisted grounded systems back then, if I recall back some of the earlier slides. So that actually was a preferred way of doing it. Solid grounding only came about, and it became part of the culture of the electrical power industry because it was a requirement by the engineers who were doing engineering within buildings. And of course, they wanted to clear the fault quickly, and they were less concerned about how impulses might affect adjacent equipment. But your mission here, because you had a special research program, required that your engineering not be off the shelf, but required a little bit more sophistication.
Yeah, that's correct. And let me just go back a few slides here. So the original system that I showed was solidly grounded. Now, of course, this is the utilities setup. These are their transformers. So, you know, we had no choice in the matter. We were given a solidly grounded system, and we went with it. And the next slide shows, you know, we bought the transformers, but we're still stuck with the solidly grounded system. And then finally we got a chance to do things our way. That's when this concept of a resistance grounded system came up.
Okay, so
not a lot of trouble agreeing, but then the issue came, well, how much ground fault current do we want? One party, I'm not sure who, wanted 1,000 amps, and the other party wanted 3,000 amps. They talked about it. They finally agreed on 1,000 amps. And again, I don't really know who won on that, or it wasn't really who won and who lost. It was just like what was the optimum current. And I unfortunately can't tell you how that decision was made. However, being affiliated with the system for the last 17 years, I'm very much in favor of the 1,000 amp value. 3,000 amps, I don't think you need 3,000 amps. I think 1,000 amps does everything you need it to do, and it minimizes the damage in comparison with a 3,000 amp grounding resistor.
Of course, you're not getting that everywhere. What's your longest feeder, and what kind of cable are you using? What kind of cable, legacy cable, are you using? EPR, 15 kV? What kind of cable?
Okay, so let's see. And another thing that was going on here in around 1989, 1990, the campus was mostly 4160 distribution, and again, because of the growth, they decided to upgrade to 12 kV. So when they did that, they put in new cable, and the standard was EPR. And I'd say 98 to 99% of our cable is 12 kV or 15 kV EPR.
Wow, so you actually recabled downstream 133%?
133, which I'll get into that just a little bit later, about 133, yep.
Okay, all right. Well, this is very, very enlightening. Thank you. Go ahead, Jerry. I mean,
okay.
But it's very interesting.
So I'm running up to 12:30, but hopefully I get a few more minutes here, maybe?
Oh, of course.
I got about four more slides or 5 more
all
slides.
the time you need. I just didn't want you to be too hungry.
Okay, great. So again, nothing changed here at the cogen plant. Gas turbines, generator, steam turbine, and our zigzag grounding transformer. Okay, so I want to take a moment here and look at the details of these grounding resistors. So this is one of our big transformers at the Hill sub at 37.5 MVA. If you run the fans, you can get up quite a bit higher. The 115 kV is coming in over here. I can't see the exact connections, but this middle bushing, that's 115 kV there. The 12 kV is coming out through this air terminal chamber here, and the important conductors, 3 phases, come up through this bus duct and down on into the building and feeds our switchgear. However, there is a XO bushing here in this box that its connection goes down through a conduit here and goes underground, comes up, and it comes up into this grounding resistor. And of course, that insulation on that cable needs to be good for at least 7,200 volts, excuse me, but I'm pretty sure it's 15 kV cable. And the reason is that when you get a ground fault, all of a sudden that XO bushing rises up above ground to, I think, can't think right now, I think it's 7,200 or possibly 12.47 kV. Let me think about it a little bit more before I give a number. But anyway, the cable's got to be insulated for full phase voltage. Next picture here, a little close-up of the grounding resistor. Note the ventilation louvers here. And I never really realized how much power has to get dissipated until I got ready to do this presentation. So it's got a 10-second rating, but the I squared R, that's 1,000 amps squared times 7.2 ohms, is 7.2 megawatts. A lot of juice has to get dissipated in this grounding resistor. That's why it's only got a 10-second rating.
I'm often amazed at how small they are when you think about it. I was even thinking about how small this was when I saw the Beatles 8 days a week and how little power they had in their amplifiers when they played in Shea Stadium. 7.2 megawatts is a lot of power.
That's a lot of juice.
That's a lot of juice.
So here's a nameplate, just a little more information. 7,200 volts line to neutral, 1,000 amps, 7.2 ohms with a 10-second rating. We did not pay the extra money to get the extended time, so there is no extended time. You got 10 seconds, and you better clear it by then. Fortunately, most of our ground faults clear well within 1 or 2 seconds. We've never had anything approach 10 seconds. Okay, so here's the grounding transformer that we use for the cogen plant. This is a little, a lot of engineers have seen these zigzags, and some haven't, so this is kind of interesting. Got 4 terminals, H1, H2, H3, and then the HO. Here's the vector diagram. The impedance, ohms per phase, you can't quite read the number, but it says 119.40 sequence. So that's the impedance. Most of that is going to be reactance. In conjunction with this grounding transformer, we have a 36 ohm resistor that gets connected between HO and ground. So that's over in the switchgear. So that provides us about 180 amps of current for a solid ground fault, which so far in my time here, every ground fault we've had has been a solid ground fault. We haven't had any real arcing, or if they arc, it's not for very much time, maybe just a few milliseconds, and then it becomes a good ground fault.
Or you mean your phase-to-phase will quickly turn to solid ground?
Phase-to-phase, because of the low resistance grounding, if we get a phase-to-phase fault or phase-to-phase-to-phase fault, three-phase fault, the ground resistors are pretty much not a factor. We get real high currents because we have nothing to limit that other than the transformer impedance and a little bit of cable impedance that we have.
Well, I mentioned that because that's always been a counter-argument against resistant grounding, but I'm not sure if this problem of picking up a phase-to-phase fault is not solved by more up-to-date instrumentation. Just putting it out there. I'm not sure if David Ship or anybody else or Sergio or others or maybe Tammy knows as to whether or not we have instrumentation now that would make up for the inability for this type of system to see a phase-to-phase fault. Do you know anything about that, Tammy?
I don't.
Okay. All right. Well, Mr. Ship.
No, actually, well, we as I'm sure many of the universities have some pretty modern protective relays. So we happen to have these Siemens Sigprotect relays. They've got really good fault recording in them. So I've got lots of records. The grounding that we have has no effect on any phase-to-phase faults. In fact, what I can see on many of the faults we've had is sometimes the ground fault doesn't last very long, and it becomes a phase-to-phase fault or a three-phase fault. And the reason is the arcing in the vicinity of where the fault occurs often destroys nearby insulation. And we get that nice controlled level of 1,000 amps of ground fault current, but as soon as the ionization happens or maybe some arcing and sputtering that burns some insulation nearby, then we get our phase-to-phase fault. And then the ground fault more or less goes away. I mean, those two phases, once they get connected, they just start pumping current to each other, and the ground system is kind of out of it. So, next slide. So there's some advantages of the low resistance grounding system, and there's really only two that I can think of, and this is a biggie. It limits the ground fault current and damage. Again, if you have 1,000 amps of current that's controlled versus on our campus we've got 26,000 amps, of available fault current, that's a three-phase fault current RMS, that's a heck of a lot less damage. I mean, just, you know, the damage goes by the square of the current. So we're talking 1,000 versus 26,000. The damage on a ground fault is minuscule compared to what we have on a face-to-face fault.
Yep.
Now here's the other thing that I didn't know about till I got a chance to be here for a while and observe some faults and analyze these fault records. And this is really important. The CTs do not saturate during ground faults on our system. Before we converted to the low resistance grounding, there were many instances of the CT saturating due to high level fault. Again, even on a prior to having this low resistance grounded system, a single line to ground fault would result in full fault current, like I say, 26,000 amps. And a lot of our CTs would just saturate, and we were getting a lot of miscoordination. We were getting upstream breakers tripping that shouldn't have tripped. Downstream breakers were not tripping, and it was a little bit of a mystery till I really started looking into this and learned a lot about accuracy class ratings of CTs and the burdens on the CTs, types of relays we're using. So this has been a really, really good thing for us in preventing saturation of the CTs. And I will mention that our fault current here is a little bit higher because we have this cogen plant sitting right on our campus. Although we have large transformers, so it would be high even without the cogen plant, but the cogen plant actually just makes it a little bit worse.
Jerry, are most of your downstream substations within buildings, they have just primary switches, right?
Yes.
All right. No breakers okay.
No, at the buildings we have these fused selector switches, so they have current limiting fuses in them.
Okay.
Okay, so now I'm to the last slide, and the disadvantages. I actually thought of 4. So here's one that most people know about. So when you get a ground fault, the voltage to ground of the unfaulted phases increases to 12.47 kV, you know, more or less. Maybe it may go a little higher because of a surge. However, with a solidly grounded system like the one we used to have a long time ago, the voltage to ground on the unfaulted phases, it remains pretty close to 7.2 kV. Again, it may get a little higher. And for this reason, we use this 133% insulation on our 15 kV cables because they're subject to a little bit higher voltage to ground because of this low resistance grounded system that we have.
Did you say you during that 20 million renovation back in 88, 89 that you replaced most of your medium voltage cabling?
Those are two separate instances. In 89 to 90 to 91, that's when we changed from 4160 distribution to 12 kV. That's when the medium voltage cable was replaced. Mm-hmm. And then in 1999 to 2000 is when we redid the substations to give us all those transformers, and that's when we implemented this low resistance grounding scheme on the transformers.
Mm-hmm. Okay.
Okay, so here's another one that you don't see in any books. We had a pretty serious ground fault here about 2 or 3 years ago. It went on for a while. When I say a while, probably 1.5 seconds, and it was pretty hefty. It was up close to our transformers. We got that all figured out. We got it addressed. But a few days later, some of our metering was reading incorrectly on our 12 kV system. Come to find out, we had blown a lot of primary fuses on our potential transformers.
Yeah.
And I started thinking about this, and I thought, well, this makes sense.
Mm-hmm.
Normally, these potential transformers are connected Y to Y, and of course, on the 12 kV system, we don't carry our neutral. So they get connected basically from phase to ground, ground being the ground bus of the switchgear. So during normal operating conditions, the voltage across each PT is 7.2 kV. However, when we get a ground fault, the voltage on the primary of the PTs for the unfaulted phases goes up or increases to 12.47 kV. And the PTs will handle that for a little bit of time, and the fuses will as well, but for probably much more than a few tenths of a second, the fuses are just going to blow. So we've had several occasions where PT fuses blew following a ground fault on the 12 kV system. It's just something we have to keep in mind.
Did you lose the PTs themselves?
No, the fuses, fuses are current limiting, fast acting. PTs were fine.
Yeah, they're often such a high ratio. They're a very vulnerable part, at least my history, our experience.
Yes.
Early in the burning phase of a new switchgear lineup, I put in maybe about 10 switchgear lineups during my time, and that was always the first place if we were going to get a failure. Unfortunately, it happened with some consistency where I can talk about it some years later. Go ahead, Jerry.
So I'll also mention some of our 12 kV switchgear uses they're called open delta PT arrangements, where you only have 2 PTs, and one of them would be connected phase A to phase B, and the other one's phase B to phase C.
Mm-hmm.
Now those are not vulnerable to these ground faults in terms of fuses blowing, so they seem to do just fine during these ground faults. It's only the PTs that are connected grounded Y to grounded Y that tend to blow fuses.
Yeah.
Okay, the third point here, very similar to the point I just made, distribution transformers on the 12 kV system should have a delta winding for the 12 kV primary and not a Y, for the same reasons as was mentioned in the step above. You get an overvoltage on the unfaulted phases if you have a grounded Y connection. And then the last issue is that the surge arresters must be rated 12 kV with a 10.2 kV MCOV. It stands for maximum continuous overvoltage. If we had a solidly grounded system, then these arresters would be of a lower rating. So, yeah, there's some disadvantages, but for me, the advantages far outweigh the disadvantages. It's been a really good system, and I'm glad we have it.
Well, I guess at the top of your advantages, we mentioned the lowering of risk to electricians.
Yes.
Right? I mean, when we're interacting with our gear, most of the time, yeah, it's true, we're working on the secondary side, but very often we're opening, closing switches when they're hot, and sometimes we don't always have the resources to exercise them according to manufacturer's recommendations. So you get farther out in the life cycle, and if I'm an electrician and I'm throwing a switch that hasn't been exercised for 20, 30 years, yeah, I'd be a little bit edgy too. So the other thing too is that your instrumentation should allow you some early warning of cable leakage. Do you have any of that on yours?
No, we don't. I've talked to people about it, but we don't have anything like that.
Okay, so I mean the ability to foresee, so to say, a leak farther upstream in some of your instrumentation, to be able to schedule an outage, that's kind of a big deal. I mean, in a research university, outages, forced outages, can run you $1 million a minute. So,
yeah, that's for sure.
Yeah, in the hospital even more. So it's, well, I'll say $100,000 to $1 million a minute, somewhere in that range. I don't think it's any less than $100,000 for a large campus like yours or ours. So, well, this has been very. There's more questions. Well, one other question, and I'm going to open it up here, that I have is the utility didn't have a problem with the resistor when you upgraded. You didn't have the utility. The utility bought. Wait a second. They are your transformers, right? But even if they are your transformers, we often will get pushback from the utilities that say we have concerns about feral residents, other phenomena you get with grounding on the customer secondary side, and they prohibit it. It strikes me that you might have had a special case because of the mission of the Berkeley laboratory. But in our morning session, we did talk a bit about that. It seems to be something that many engineers run into when they're dealing with a high voltage service with the utilities for a campus power system.
Yeah, so they did not have any problem with the grounding resistor here on the secondary, but they did dictate that the primaries had to be a grounded Y configuration. We had to run our design by them, and they certainly could critique it, and they could tell us what was allowable and what was not. But I'm told that because of this cogen plant down here, all of these transformers had to have a grounded Y primary on them. I think I haven't been too involved with picking out transformers before, but you might want to normally pick out a delta winding for this 115 kV, but PG&E insisted on a grounded Y, so that part they did have influence on us, and they told us what they wanted, and we had to go with it.
I'm sure they've thought it through, and it's worked. I know that uh, I've heard over at Consumers Power in another part of Michigan that they also have dealt grounded Y primaries, but they observe a fair amount of ferroresonance. I'm sure they got that figured out. It's a good system. I guess what I'm going to do is open the floor to questions. I see a Keith LaForgia came on. Keith, I guess maybe before we go into questions, I should. Are you able to introduce yourself, Keith? Let's see, Keith LaForgia. Maybe he doesn't have a microphone. Okay. Let's see who else. I still have 3 other callers. We have 8 people on the call here today. So I'll open it up. Tammy, Lauren, Kane, anyone?
I'm not very knowledgeable about resistance grounded systems, but one thing I was wondering is, have there been instances when you have low-level faults perpetuating for, a long period of time?
I would say no. My experience, not just here, but at my prior job, was on 12 kV. If there's a fault, it's going to go to the maximum level pretty quickly. At 12 kV's got just so much potential behind it that it doesn't tolerate much. In my experience, it doesn't tolerate much with intermittent fault or faults that only bleed a few amps or something. I mean, every time I've encountered a ground fault, it goes fairly quickly.
That makes sense. So basically, at this voltage level, when you have a fault, you know it, and it's that simple.
Yes. Uh-huh.
Do you know why the decision was made to go with low resistance grounding as opposed to high resistance?
Is this Keith? Yeah, Keith, I covered that, but maybe you weren't here. So, yeah, there were lots of discussions between the Lawrence Berkeley Lab people and the University of California people here, collaborative discussions, and one party wanted to limit the ground fault current to 1,000 amps, and the other party wanted to limit it to 3,000 amps.
I heard that high resistance grounding would limit it to something like 30 amps.
Oh, yeah, I think you might get into a little trouble with voltage excursions if you put high resistance grounding on the 12 kV system. I don't think that's recommended for 12 kV. You might get by with it at 480, but 12 kV, in my experience, every time somebody uses resistance grounding, it's going to be low resistance grounding. And yeah, you have to look at the current, but you have to look at what happens to the voltages as well. And with those high resistance grounding schemes, yeah, the 12 kV voltages to ground, I believe they can climb even higher than what they are with the low resistance grounded system. Those are for the phases that are unfaulted.
The reason I asked is I just want to make sure I understand. So with the high resistance grounding, with the low resistance grounding, with the neutral grounding resistance that you have, it's only got a 10-second rating. So basically, you must clear that fault. So you're still in a situation where you must trip, just like you would be in a solidly grounded system.
Yes. Uh-huh.
Was that Keith or was that Lauren?
That's Lauren.
Oh, I'm sorry. I thought you were Keith.
I recognize Lauren's voice, yeah, from Alberta. Or Edmonton, right?
Yeah.
Yeah, okay.
Your generators, what?
Seem to have lost him.
The generators, what voltage level?
Those are 12.47 kV.
Do they have unit transformers, or are they directly connected onto the system as you've shown in the single line here?
Those are directly connected. So the distribution is 12 kV, so they just feed right into the distribution system.
Well, that's very interesting. We've got a couple of generators on my campus, and we do have unit transformers for them, even though they're basically a 1-to-1 ratio. And we did that to limit fault current and to provide some voltage stability as well.
We do have some current limiting reactors that I didn't show, but they'd be here on the diagram. They help a little bit with lowering the amount of fault current that comes from the cogen plant when we have a fault.
Okay, interesting.
Jim, you have any thoughts? I think I'm seeing him. There he is.
Yeah, yeah, I'm here. I'm here with Keith LaForga, our electrical engineer also.
Oh, okay. I'm seeing
Hi guys.
Keith. Do you want to say a little bit about what you do? I guess all three of you guys are out in Berkeley today, right?
Yeah.
Yep.
My name is Keith. I've been here with the lab for a little over 5 years. Actually, the SME for the medium voltage systems here on site. So, yeah.
Well, this is probably it strikes me as one of the more enlightened power systems. Of course, it helps to have some catastrophe as a driver. That'll loosen the money you need to do it right. I bring this up because we're on the leading edge, or I guess the front end of what I'll call the smart campus zeitgeist. That's my way of saying is that we're getting a lot of discussion among the leadership. How can our campus be smarter? And of course, usually that involves more retail, consumer level type of activity. But farther upstream, I don't want the possibilities I don't want to overlook possibilities for making improvements upstream, where we have a chance to insert ourselves into the discussion. I try to remind the leadership of the education industry that the smart campus transformation is essentially electrotechnical. And if we know better ways of evolving our power systems, that we ought to at least discuss them. It may not be applicable everywhere. Certainly safety is a large driver for all this. But what I don't want to see have happen is to see us build inefficiency upon an existing inefficiency because all of the possibilities were not laid out for the leadership. I don't know. I know this stuff is not cheap, but I also know that research universities are a central part of the American economy. They're not going away, and they're going to need to be more sophisticated. And I'd like to see the next leg of development to be informed by some of the possibilities. As Jerry knows, and some of you know, I've been very active in the NEC for the past 20 years, trying to make campuses safer, simpler, lower cost, and longer lasting. And it strikes me that here's a chance for us to advise the leadership of the industry that you can make your campus, the power system, more reliable. It strikes me that with medical centers going up the way they are, it's a fairly large part of most universities. By the way, Jerry, does UCal Berkeley have a hospital, or is that just UCLA? Who has a hospital?
We don't have one. UCSF has one, UCLA, and I believe UC San Diego.
Yeah, okay. But Texas and Carolina, they all have monster academic medical centers, and so it strikes me that this is what we want to be able to have at least be an understanding among ourselves, and there's not many of us, of course, about what the next leg of development might be. So that's kind of all I wanted to say. We have run into an hour here. It's been very productive for me and others. As usual, we are not able to get to other parts of the E&H committee agenda. So what I try to do, and I explained earlier this morning, as Jim heard, is that our bi-weeklies that we have in Europe as well as in America, of course, are meant to just do presentations like this and to sort of sort through our priorities. What we typically have to do is when we want to focus on something, we need yet another teleconference. And so that's my lead-in into giving Tammy the floor to explain what her project is all about, and the breakout meeting that we're going to be having next week. So before I do that, I wanted to take control of the screen again, Jerry, but I wanted you to have one more time. Is there something else you'd like us to see here before I take control of the screen again?
No, that's all.
You have it? Okay. Okay, so I'll take the screen again, and we'll let Tammy talk a little bit about her project. Let me get it going here. So here's our page. And Tammy, could you please speak a bit while I'm picking around to get the web page? Say what you'd like to have done, and we set that meeting for the 28th. And describe your project a little bit just to bring Jerry and Jim and Keith up to date. Lauren already knows about it, and then I'll find the page so they know where we're going with this. Go ahead, Tammy.
Okay, basically I'm working on phase 1, just a small part of this project, and the project is on evaluating electrical feeder and branch circuit loading. I think it's a really important project, and I just have the initial part, which is simply a literature review and to develop a data collection plan. That's why I feel like, although it's small, my project is probably more important than the larger project, which is the collection and analysis plan of the data. And next week, those of you who have time, I would really appreciate you spending the time with me and us talking about the data collection plan. I actually had envisioned a very small project. I kind of thought of a phase 2, but what I need to do is to develop a large plan which is going to help us evaluate actually it's Articles 210 to 230 in the National Electric Code, and those provide the design requirements for branch circuit and feeders. And what you all know probably, because you're well acquainted with Mike Anthony, is that there's been some research done that he's done, and he's found that there are a lot of losses associated with the current NEC design requirements. And so the goal here would be to collect data on branch circuits and feeders and find out what their percent loading is. Is that I know some of his papers have indicated that transformers are grossly underloaded. Now, it's my perception that I agree with him, but what I'm wondering, I'm kind of I don't know, maybe antagonistic to things, but what we really need to see is what's going on with existing construction. I mean, like new construction in the last 2 years. What are our loadings? Because if they're really low there, then that's a real sign that there are a lot of energy losses going on, and that maybe the NEC design requirements could be rewritten in a way that would help us save a lot of energy costs. And there's also a lot of other things associated with that. But anyway, I won't keep you unless you have any questions, but I have a lot of problems on how to set up a good plan, because if we just, evaluate feeders, we're not going to see individual loads. Actually, even just evaluating individual panels supplying branch circuits, usually panels are fed more than one type of load. So for example, how are we going to know what the lighting load is? How are we going to know what the receptacle load is just by evaluating feeder data? And that's what the NEC is doing. I mean, it's specifying the specific loads for lighting, receptacles, and, the various main categories of loads in a system.
Well, as I mentioned earlier on, that Jerry was generous with his expertise. We used some of his data, and some of that data was piped into the substantiation for getting the 2014 code change. And I'll try to hurry along here. So, in 2014 we got an exception to the lighting table, and in 2017 we actually got even more. We got even the committee to agree to even more permissive statements in Article 220 that would allow you to change to make the to what we call right sizing the transformer. And so what the table that she's talking about is right here. This is the exception that we got in last time, and this is important because this is determining the size of your power system. When you roll in and you say I think Jim was talking about the expansion of the lab. Now we all came to understand that the lab itself was a different type of occupancy. But for most building in higher education, we're using this table for lighting loads, and we're finding the ASHRAE is telling us you need to stay at 3 watts a square foot. NEC is making us design for 3 watts a square foot when ASHRAE is limiting us to 0.9. Something's wrong with this. So I don't think I have to. Preach. I think I'm preaching to the converted here. Jerry also observed that his transformers are at least 50% loaded and below. They're on day one. Of course, they're usually low anyway. But even farther out in the life cycle, it's rare to see a building level substation more than 50% loaded. Did I quote you correctly there, Jerry?
Yes, with just one exception. Yep, and we looked at a lot of transformers, but yep, that's true.
Yep. And I'll close right here with a little anecdote which surprised me quite a bit. Where we're going with this is, and why we needed to, and I have to see if I can zoom in on this. This is the offending number right here. You see that 180? Do you want to say a little something about how long ago that number was established, Tammy?
Yeah, it was actually established in 1936, and that goes to show you what happens with engineering precedents. And people say, well, I'm sure it's for a good reason because we've used it for a long time. But I think it originally started out related to the lighting load, and yes, it is the receptacle load. But I think that somebody determined that 120 volts by 1.5 amps was a good number, and that's how it came out based on a lighting load. Okay,
well that's maybe when they had more lighting in incandescent lights. So, okay, so this needs to be changed, and that's what that meeting next week is all about. We're going to drill down into how we scope a larger research project to start approaching these tables and basically rewriting them. We're talking about rewriting large chunks of the National Electrical Code. We don't do things small here, do we? Of course we don't, Jerry. So, no. Guys, I guess I'd like to leave you here on our. I'm very grateful for your time. The rest of the industry is. I'm obligated to tell you that I hope you can do another version of this at one of these IEEE conferences. These are very helpful teleconferences to get people to exchange information that can't get to the conferences. But if ever you have a yen for wanting to do a paper or to talk at length and expand your presentation and to travel to foreign parts, if you want to go to Frankfurt, Jerry or Jim, let me know and I'll send you a letter to your boss to say I think you should be at this meeting in Frankfurt. Talk all about the Berkeley power system. Would that interest you?
Not this particular one, but possibly another one. I'll be gone that time anyway on vacation, but possibly in the future.
Oh, I'm joking. That's the trouble with teleconferencing. Oh, but I want you guys to think big, okay? So that's why I brought that up. Okay. Anything else? Anyone? Okay. So the next teleconference will be here. Excuse me. What we have Tammy's teleconference, but the next E&H session. It's a formal business meeting here in Portland. So thanks very much for your time, colleagues. Be safe, and we'll see you in a couple weeks on the Worldwide Inner Tubes.